After this short exposure on mathematical modeling of physical systems, let's get back to our motor control problem. What is it that we are going to model there? Our problem consists of driving a mechanical load by the separately excited DC motor. What are the various parts of the motor and of the load for which we can write down equations, and then perhaps we can combine them into one or more equation. I mentioned the armature winding of the electric motor, and the same holds for the armature winding of a DC generator also. In fact, as you perhaps know already, the same machine can be used either as a motor, DC motor, or as a DC generator. In a way, there is no basic difference between the two. In both cases, magnetic field or flux is involved, current is involved, rotation takes place, torque is produced. The only difference is that in an electric motor, the power is drawn from an electric supply and mechanical power is given to a load, whereas in the case of an electric generator, the power is drawn from a mechanical supply such as a turbine and is delivered to an electrical load such as an air conditioner or a heater or what have you. So if one looks at the armature winding of the motor or generator, one can use a crude but fairly good model for the behavior of the armature winding. The armature winding is of course made up of series connection of a large number of conductors which are located in slots on the armature. So we can think of it as one single long piece of wire wound around a magnetic core material. Now when this armature with the winding on it rotates in the magnetic field produced by the field winding, electromotive force is produced. That is, the winding looks as if it is generating electromotive force. And there is a simple relationship between the EMF or the electromotive force that is produced in the winding as a result of the motion of the conductors in the magnetic field, the magnetic field itself, and the speed of rotation of the armature. We are assuming that the magnetic field current is kept constant, and therefore the magnetic field to a good approximation will remain constant. Constant in the sense, at a given point in space in the air gap, the magnetic flux is not going to change with time, although at different points of the air gap the magnetic flux density will not be the same. Under this assumption that the field current and therefore the flux or the field density is kept constant, the back EMF, as it is called, or the EMF produced in the armature, will be simply proportional to the angular velocity. In a way, the armature behaves like an inductor, and you will recall Lenz's law or Faraday's law and Lenz's law together, that whenever there is a change of current in an inductor, the inductor tries to oppose it, so to speak. That is, in the inductor an EMF is produced proportional to the rate of change of current, which opposes the EMF which drives the current through it in the first place. In exactly the same way, the armature winding rotating in a magnetic field produces this EMF, and this EMF has a particular direction, and for the machine to run as a motor, the applied for EMF or electromotive force or voltage will oppose this generated EMF, and therefore this EMF is called the back EMF, EB. And therefore we'll start writing down our first equation for the armature, namely the back EMF EB produced in the armature winding is proportional to the speed of the motor, omega m, m for motor, and there will be a constant of proportionality relating the two, and since we are talking about the back EMF, this constant will denote it with a subscript b. So we have the simple relationship, the back EMF EB is equal to KB into omega m, where omega m is the motor speed. This KB is therefore called the back EMF constant or coefficient of the motor. Since the back EMF will be in volts, or if it is expressed in volts, and omega, the angular speed, may be expressed in RPM or radians per second, so the back EMF coefficient or constant will have the dimensions of volts per RPM or volts per radians per second. For a given motor then, with a given field current, or the field current is also referred to sometimes as the excitation, and that's why the motor was called, or is called, separately excited motor, that it gets its field current from a separate source of supply. This KB will depend on the field current, of course. So for a given motor, for a given field current, there will be some particular number KB or value of this back EMF constant or back EMF coefficient KB, and the back EMF produced in the armature as a result of motion will be given by EB equal to KB into omega. There is one more equation, that electrical equation, that we can write for the armature, and this is because of the fact that the armature is connected to a source of DC voltage or DC electromotive force, or the supply voltage. The supply voltage we will denote by capital E, sometimes with a subscript A to remind you of the applied voltage. The machine is to run as a motor, so you have to apply a voltage to it rather than get a voltage and power out of it. So EA is the applied voltage. There is this applied voltage, and of course, assuming that the motor is somehow rotating, there is the back EMF produced in the armature, and these two would be equal and opposite in their directions, but for the fact that in general there will be a current flowing in the armature, and the armature winding is a long electrical wire and therefore has resistance, and therefore as a first approximation, which is fairly good, we can write down the following equation. The applied voltage is equal to the back EMF produced in the armature winding plus a term that corresponds to the fact that the armature winding has a resistance, and therefore this term, as given by Ohm's law, will be RA into IA. IA, as usual, will denote the armature current. RA will be the armature resistance. We can take the machine and instead of using it as a motor, we could drive it by some mechanical means, that is, rotate its armature at angular speed omega, not connect anything electrically to the armature winding. Then with a voltmeter we can measure the voltage EB, the back EMF, and at that time no current will be flowing in the armature. Therefore the armature drop, as it is called, the term RAIA is called the armature drop. This will be 0 because there is no armature current flowing, but the back EMF is produced, and the back EMF can actually be measured. This is referred to sometimes as the open circuit test of the machine. And in your machines course you might have carried out an experiment called the open circuit characteristic of a DC machine. You turn the machine somehow, and for various values of the field winding current and various speeds of rotation, you find out the open circuit voltage that is produced. And the open circuit voltage is reasonably proportional to the speed, therefore this constant Kb. So the constant Kb can be actually found out by this open circuit test. However, when the armature is connected to a DC power supply or a voltage source, you have the back EMF Eb and you have the applied voltage Ea, and if the armature is not being driven externally, it will function like a motor, in the sense the applied voltage Ea will be greater than Eb, and therefore there will be an armature current flowing in the armature, and therefore we will have the equation Ea equal to Eb plus RAIA. There are some other phenomena that take place in the machine. There is something known as armature reaction, because the magnetic field that is produced by the field winding current continues to exist, but the armature current itself produces a magnetic field which cannot be ignored, and therefore this phenomenon called armature reaction takes place. We will ignore it. We will simply assume that the armature resistance can be taken care of by this armature drop RAIA. Now I said Ea is greater than Eb because you can see what is happening. You can think of what is going to happen when the armature is stationary and you apply a source Ea. At that time there is no rotation, therefore there is no back EMF produced. The term Eb is equal to 0, and therefore if there is no additional resistance connected in series with the armature, a very large current will flow given by Ea divided by Ra. The applied voltage may be of the order of hundreds of volts, let's say 230 volts. The armature resistance would be of the order of at most a few ohms or even less than an ohm. And so you can see that if to a motor at standstill you apply the full supply voltage, a large current will start flowing because there is no back EMF, there is no rotation. So Ea is greater than Eb because Eb is 0, and therefore current starts flowing. Now this current, because it is in the presence of a magnetic field, therefore results in the production of a force on the armature conductor, and because the armature is mounted on a shaft and capable of rotation, the armature will start rotating. Now as soon as the armature starts rotating, of course a back EMF is produced, and if one looks at the appropriate rules that are involved that give you the direction of the back EMF and the direction of the torque or the force that is produced, it will turn out that Eb will start increasing and will be in a direction opposite to Ea. As a result, the armature current will reduce from the original very large value, and as the motor speeds up, we are assuming that a torque is produced and the torque is greater than the load torque. In fact, the starting torque of the motor, if the motor is started without any resistance, can be very large, and therefore the motor will begin to accelerate, and as the motor picks up speed, the back EMF increases, the difference between the applied voltage and the back EMF, which can be thought of as causing the current, armature current, will go on decreasing. Because of the decrease in the current, of course, the torque that is produced will also be reduced, till finally the situation is reached when the speed and the armature current are such that the back EMF produced with the armature drop is exactly equal to the applied voltage, and the torque that is produced exactly balances the load torque, and therefore the load and the motor does not accelerate anymore and runs at a constant speed. We have written down therefore two equations for the electrical part, the back EMF equation EB equal to KB omega m, and the electric circuit equation for the series circuit, as it were, of armature resistance, the back EMF, and the applied voltage. However, as we have seen, the armature current may not remain constant, because the load may change, because the supply voltage may change, among other things, and therefore armature current may vary with time. Now, when it varies with time, then there is an additional term or factor that we must consider, and I told you that the armature can be thought of as some kind of an inductor, because ultimately it consists of conductors in the presence producing a magnetic field, because they are in the presence of magnetic material. Of course, these conductors are in the presence of a strong magnetic field produced by the field winding, and therefore the equation will get modified as follows, and I'll write it in such a way that every term perhaps could change with time. The applied voltage EA at time t equal to the back EMF, and the back EMF will write therefore as kV into omega m at time t, plus RA into IA at time t, the armature drop, plus one more term which can be thought of as some kind of an inductive, self-inductive effect of the armature, and therefore LA DIA dt. This will be the total electrical equation for the armature. Applied voltage consisting of three terms: the back EMF, the armature voltage, armature drop, and the inductive effect because of changing armature current. As I said earlier, this is all an approximation for the actual behavior, but it's a reasonably good approximation, or at least one can make this approximation, make some calculations, and see what happens actually by going to the laboratory and doing tests. Incidentally, all of you should, if you have not already seen an electric motor, should go to the laboratory and have a look at the DC motor and see it in operation. This is for the electrical part of the armature. Remember, I am assuming that the field current is somehow maintained constant. So there is no equation for the field current or for the field winding. We will simply say that the field current IF as a function of time t is just some constant value. It's not changing with time. Later on we will consider the possibility of changing the magnetic field or the field winding current. So right now the kind of control action that we are thinking of does not involve changing the field current, but could involve changing the applied voltage EA, and therefore this is referred to as armature controlled motor or armature controlled situation for a DC motor, separately excited DC motor. If the field current can also be changed through some arrangement, instead of the armature applied voltage being changed, then one refers to it as a field controlled motor or field control of the speed of the motor or of the drive. So at the moment we are looking at armature controlled drive. What about the mechanical part of the armature and the load? Here again we'll make some simple assumptions which may not be valid in some particular cases. The armature is wound on a core, it's quite heavy, it's mounted on a shaft which is going to be rotating, and at the other end of the shaft I am assuming that you have a load such as a grinding wheel or maybe a pulley which through some belt drives some mechanical machines and so on. You could think of even a flywheel at the one end of the shaft. So what I am implying is that there is a rotational motion of not only the shaft but also the armature, the load, and therefore one has to consider the moment of inertia of this rotating part. If there is no gear train, the load is directly driven, then we can combine the moments of inertia of the armature, that is the motor, rotating part of the motor, and the load itself under a single moment of inertia. And the symbol very often used is J, capital J. If one has to talk about the motor moment of inertia separately from the load moment of inertia, then one will use two symbols, Jm and Jl, M for motor, L for load, as before. But for the moment let's assume that there is no gear drive, the shaft is directly connected, and therefore we are talking of a single moment of inertia, and therefore I will denote it by J. Now the dynamical equation for the rotational motion, as you know, is similar to the Newton's equation for motion of a particle, namely mass into acceleration is the total applied force. So here then we will have the moment of inertia J multiplied by the angular acceleration, and since we have denoted the angular speed by omega m, therefore we will have it as d omega m dt. This will be the accelerating torque, that is, this will be the torque which is related to the acceleration of the motor. Of course the acceleration may be positive or negative, one uses the word in a neutral sense. Omega m may be increasing or omega m may be decreasing. So this is the torque which is required to accelerate or change the speed, rotational speed of the shaft and the armature and the load, all of it having a moment of inertia J. Now this, where is it coming from? What is accelerating or what is turning the shaft in the first place? The force that is produced by the interaction between the armature current and the magnetic field, or that is the torque which is produced in the motor. And as I had indicated earlier, we will use the letter capital T for torque and M for motor, and therefore we can talk about the motor torque Tm. Now once again, it's a fairly good assumption to make that the motor torque Tm is proportional to the armature current. Of course the motor torque is the result of the interaction of the armature current and the field or the flux density, and therefore it's also going to depend on the field. But we have assumed that the field winding current is kept constant, and therefore the motor torque produced Tm will be proportional only to the armature current, and therefore we will write the equation Tm is equal to K subscript T, to remind us of torque, multiplied by armature current Ia. This Kt, for an obvious reason, is called the torque constant of the electric motor. It relates the armature current to the torque, and so its units will be, torque is Newton meters, current normal unit is ampere, so Newton meters per ampere. So this is the equation for the production of torque in the motor winding. Tm equal to KTIA. Of course, I said that we will have to consider the situation when the armature current is not going to remain constant, and therefore Ia will be a function of time. Then the motor torque also will vary accordingly, and therefore I'll write Tm of T equal to Kt, the constant, torque constant, into Ia of T. This is an equation which is not a purely electrical equation, it's an electromechanical equation, and this is one of the two equations that reflects the fact that the electric motor or the electric generator or the induction motor, DC, AC, what have you, they are all electromechanical systems. They involve both electrical as well as mechanical variables. Torque, mechanical variable, rotation is related to armature current, an electrical variable, and the other equation of course was the very first one that we wrote, namely the back EMF equation. We have EMF or voltage that is produced, an electrical quantity, and a quantity related to the motion, namely angular velocity, omega m. So these are the two equations of electromechanical interaction, and right now we are looking at the torque equation. Torque is equal to Kt into Iat. This torque constant can also be measured experimentally, because it's a little harder to measure than the back EMF constant. Electrical measurement of voltage is much easier than measuring torque on something which, in fact, if it is rotating, it's even more difficult. So what is done is the motor is forced to remain at rest. So the motor winding or the armature shaft has to be clamped, and then some force will be produced on it that will be counterbalanced by some other force which is measured, and so on. So these are referred to as dynamometer tests, and some of you in your machines course may have done such tests. So from such tests the value Kt can be obtained. Now again, it's a fairly good practical approximation, and one can show that in ideal theory it must be true, namely that these two constants, the back EMF constant which relates EMF to speed, and the torque constant which relates the torque produced to the armature current, these two are equal. Their units look different, volts per RPM or volts per radians per second and Newton meters per ampere, but if you look at the dimensions that are involved, you will see that dimensionally they are the same. You should do this yourself. This will also give you some practice of looking at dimensions of physical quantities. So look at the dimensions of torque and electric current. Electric current can of course be taken as one of the fundamental dimensions, or you could take charge as a fundamental dimension, and similarly voltage then may be a derived dimension, and angular speed of course has a certain dimension, and you can check dimensionally that Kb and Kt will have both the same dimension. There is also an interesting effect or a corollary of this relationship Kb equal to Kt, because if I take the equation Eb equal to Kb omega m and take the equation KTIA equal to Tm and take the product of the two equations, then I will get Kt into Eb into Ia equal to Kb into Tm into omega m. Now what do the two terms on the two sides of this equation mean? The variable terms. Kt and Kb are coefficients, Eb is EMF or voltage, Ia is current, so the product can be thought of as electric power, volt amperes or 1 volt and 1 ampere will give rise to an electric power, in this case DC power of 1 watt. On the other side you have torque, Newton meters, and angular speed, and their product is also power. That's the power in mechanical engineering or in a mechanical system. And so you have electric power on one side and you have mechanical power on the other side. Now if Kt is equal to Kb, this means that these two powers are equal. Because if this equation is true, Kt Eb Ia equal to Kb Tm omega m, and of course it is true, then if Kt is equal to Kb, we can cancel off that factor, and therefore we will get Eb Ia equal to Tm omega m. That is the electric power. That is, if one looks at the motor from the electric aspect, there is the back EMF Eb, which is very nearly equal to Ea, multiplied by the armature current. The electric power is equal to, if you look at the mechanical side, there is a torque Tm and there is rotation at omega m speed, and therefore there is a mechanical power Tm into omega m. So this is some kind of conservation of power, or better, it is a transformation of power, as one would say, from electrical to the mechanical, and therefore the motor is a electromechanical energy conversion device, converting electrical power into mechanical power. Whereas an electric generator will act in the opposite direction. It will convert mechanical power into electrical power. This suggests that Kb and Kt may be equal, and as I said, if you go into the theory of it, then under certain ideal conditions one can actually prove by calculating the forces and the EMFs using the appropriate laws and equations that these two coefficients must be equal. But we will continue to use the two symbols, although it should turn out to be the case that these two are nearly equal, if not absolutely equal. And of course both of them are dependent on the field winding current. It's for the same field current or field winding current that I will talk of Kb and Kt, and then they will be equal. If we change the field current, the torque production will change and the back EMF production will also change in the same, by the same factor or in the same proportion. So for the same field winding current, Kb will still remain equal to Kt. Okay, so this is the torque production equation. What about the load now? Going back to the load, we had talked about the moment of inertia, J, of the whole system. There is this motor produced generated torque Tm. Now the load itself, we could think of it as something which opposes the motion of the shaft. Actually we want the load to rotate, but there is some opposition to its rotation somewhere. Think of the grinding wheel example. The grinding wheel is mounted on the motor shaft and the grinding wheel is pressed against some surface which is to be machined, and there is resistance to that motion. So there is a counter torque, or rather the grinding wheel must be applied certain torque for it to rotate. The surface being machined is opposing this motion. Therefore in this sense we can talk about the load torque, and therefore Tm will be equal to TL, the load torque. For example, the action of the grinding wheel requires a certain amount of torque. It will depend on what the material is and how far you have pressed the grinding wheel against the surface and so on. So there will be a load torque TL, and of course if the speed is not remaining constant, there will be the moment of inertia term T J into d omega m dt, and in addition the shaft is mounted in some bearing. There may be a cooling fan on the motor shaft. As the fan rotates, there is resistance of the air. So all of this we can think of as some kind of friction, and therefore an opposing force to the rotational motion of the shaft and the armature. If it's a fan, then it's referred to as the windage. It is the air resistance which requires some electrical power to be supplied to the ceiling fan. Otherwise, the ceiling fan would rotate without any power required. But it has to move air, and therefore there is this resistance to movement, which is called windage. So this windage plus friction in the bearings, again, it's not a bad approximation to assume that all of this is a torque which is proportional to the angular speed. And therefore, I'll use one more coefficient, Kf, F of friction, into omega. Omega is the angular velocity of the shaft. So this is the mechanical equation for the drive. The generated torque, the torque generated by the force acting on the conductors, equal to the load torque, the opposing torque somewhere, grinding machine, lathe, what have you, plus whenever there is a speed change, there is this accelerating or decelerating term, J d omega m dt, and there is the inevitable friction, and therefore we have an opposing torque due to friction, which we are modeling by Kf into omega. So with this we would have completed writing down the equations for the motor, and let's look at them all together once again. The back EMF equation for the motor is Eb equal to Kb into omega m. Both of them may be varying with time. So Eb of t equal to Kb into omega mt. The electrical equation for the winding, once again, because the current may be varying with time, will be EAT equal to Kb into omega mt, the back EMF term, plus RAIA of t, the armature drop term, plus LA into the rate of change of armature current, the inductive effect of the armature winding. That is the effect of the fact that the armature itself produces a magnetic field. Then the electromechanical interaction equation, like the back EMF equation, the other equation, torque, motor torque produced is equal to Kt into Ia, and the mechanical equation for motion of the system, namely the motor torque equals the load torque TL plus the accelerating torque J d omega m dt plus the frictional opposition torque Kf into omega. So these are the equations with which one will then have to start thinking about the control of the speed of the motor or whatever one wants to achieve. What are the various physical variables that are involved in our model? Armature current, of course, Ia of t, the applied voltage Ea of t, the external voltage DC power supply voltage that is applied to the armature winding Ea of t, the speed of rotation of the shaft omega m of t. If we have a gear train, then we'll have two separate speeds, the motor speed, the load speed. We are assuming that it's a directly driven load for simplicity, so there is only one speed to talk about, omega m or omega L, the shaft speed. And of course there are other variables. These variables IAT of course can be measured. Simply connect an ammeter in series with the armature, you can measure the armature current. The applied voltage can be measured with the help of a voltmeter, no problem about that. Angular speed, how does one measure the angular speed of a rotating shaft? One could use what may look like more mechanical devices for measuring speed, but since we are already dealing with an electromechanical system, namely a motor, one might use the system in the opposite direction. In other words, have a generator mounted on the shaft which produces a voltage which can then be measured, and in fact this is what is usually done. You have a very small generator because you are not interested in producing power, you only want to get an indication of the speed of the motor. That is, you want to measure the speed of the motor. So a small DC generator is mounted on the same shaft, and because it measures speed, the Greek root for the word speed, tachos, is involved. This generator is called a tacho generator. It's essentially a small generator which is mounted on the shaft of the motor, whose voltage, DC voltage, will be proportional to the speed, and therefore it gives you a simple in a way, simple means of measuring the speed of the motor or the drive. And it's useful because it's voltage, and things can be handled more easily with electricity than with mechanical things. As you know, voltages can be added or subtracted, amplified, reduced or attenuated much more easily than what can be done with mechanical quantities. So these are the three main variables then: the armature current IA of t, the applied voltage EA of t, and the angular speed omega m of t. There are of course other variables. There is the load torque TL, and I should put a T there also, because that can be a culprit. The load torque may change, and therefore I should think of it as a function of time, and in fact therefore it is one more variable that is important. The grinding wheel in action, the surface is changed, the pressure with which you or press against the surface could be changed, the quality of the grinding may be changed. As a result, there will be a change in load torque. So this is an important variable, TL of t. And there are the other variables which it's not really possible to measure that easily while the motor is operating. One is the back EMF, EB. I told you that you could measure the back EMF when the machine is not run as a motor actually, but is driven somehow, and the armature is not connected to anything, so you measure the open circuit voltage. But we are now operating the machine as a motor, so there is no longer any possibility of measuring EB. If you connect a voltmeter across the armature, what you will measure is the applied voltage EA of t and not EB of t. Similarly, the generated torque Tm, that's going to be not so easy to measure. It's not going to be easy to measure the force on the conductor or the torque that the armature or the shaft transmits from the armature where it is produced to the load where it is used up, so to speak. Now of course torque can be measured, and some of you may have been exposed to a little bit of mechanical engineering to realize that when a shaft like this one transmits a torque, that is, one end of it is the motor and something, the electromagnetic effect is pushing the thing round, and at the other end is the load which is opposing this motion, and a torque therefore is being transmitted in a shaft. The shaft undergoes a twist. It may be very hard to believe. You may think of the shaft as something very rigid, but it is both a matter of fact as well as theory that the shaft undergoes a twist. Just as in our earlier example of a mass spring dashpot system, if you exert a force on the spring, if you pull it, it will stretch. If you push it, it will compress. So similarly, when a shaft is transmitting torque, one end of it is turned, and as a result the other end also turns. There is a twist in the shaft. Now this twist can actually be measured. It's not so very difficult. Easier to measure the twist than to measure the torque being transmitted. And now something like the rotational version of Hooke's law will tell you that the twist is proportional to the torque. Just as for the spring, the force was proportional to the extension, there is a rotational Hooke's law which can be used, and therefore the torque generated by the motor can actually be measured. Of course, what is really measured is torque that is transmitted at any one particular cross section of the shaft. By using things like strain gauges and so forth, this twist can be measured, can be converted into a voltage finally as usual, and therefore the motor torque or the torque at that section of the shaft can be measured. But it's not so easy. It's not as easy as measuring the speed of the shaft simply by having a tacho generator and looking at its output. Okay, so we have these four variables of importance besides the back EMF and the torque that is produced at every moment of time. And we have to know the values of the various parameters that are associated with the drive. There are motor parameters, there are the two constants Kb and Kt, which will be nearly equal for a given field current, of course. There is the armature resistance Ra, there is the armature inductance La, which we must know. These are the electrical parameters. Of course, Kb and Kt are the electromechanical parameters of the motor. And then for the load and the armature thought of as a single rotating entity, we need to know the moment of inertia J and the coefficient of friction Kf, relating the torque, the opposing torque caused by friction, to the angular speed omega. So these are the parameters that we need to know before we can use these equations to design a control system. This is of course a very simple modeling of the separately excited DC motor. We have made many assumptions or approximations, but it's a good enough model to start with, and it's not that simple because we have equations which are no longer simply algebraic or arithmetical equations. Back EMF is proportional to armature current is simply arithmetic, but the electrical circuit equation already involves a derivative of the armature current, and so it's more complicated than a simple arithmetical equation. As you can therefore expect, there is a little bit of calculus or derivatives are coming in here. Similarly, the motor torque produced is proportional to the armature current. That's very simple, but the mechanical equation is again something that involves a derivative of the angular speed. Of course, the angular speed itself can be thought of as a derivative of the angular position, but in our modeling we are not worried about the angular position of the motor shaft, simply because I am assuming that the application is such where the motor shaft is to go on rotating. The whole idea is that the grinding wheel should be rotating and not simply to be put in some particular position. We are looking at a speed control system. Omega is our variable which is to be controlled, the motor speed. Later on we will see an application where the same DC motor could be used for position control. There the purpose of the motor will be not to make something rotate at some constant speed or change the speed, but to put it in some particular angular position. This should remind you of something we discussed earlier, namely a gun which is being controlled with the help of a radar. An enemy aircraft is being tracked by means of a radar, and the gun is to be pointed as closely as possible at the target. Therefore the gun has to be moved. The gun will not be rotating continuously, but the gun will change its position, and which can be achieved by a motor. In fact, two motors will be required because the motion is in a horizontal plane, a motion in azimuth, as well as a motion in a vertical plane, that is a motion of elevation or altitude. So not one but two motors will be required, and that will be a position control system. But right now we are looking at a speed control system. Let's write down the two equations which involve the derivatives. using the notation that I had introduced earlier, namely D as the operator or the symbol that denotes the operation of differentiation or taking the derivative. So if we do that, then the electrical equation will look like EA of T equal to KB into omega m T plus RA IA T plus LA into derivative of IA at time t. So everything is at every moment of time or instant of time t. The applied voltage at time t at a given instant of time t is the sum of these three terms. Instead of writing this t on both the sides, we could write this as an equation as follows: EA equal to KB into omega m plus RA into IA plus LA into DIA. Such equations are not very commonly written in many control books. You will find that the equations have that T standing out all the time. So why am I writing this equation? Well, this equation, as we will see later on, can be interpreted a little differently. The earlier equation where that T appears says that at every instant of time something is happening, whereas this equation in which the T has disappeared is now an equation that involves not instantaneous values, because there is no T there, but involves functions. Of course, these are functions of time, that is, we are interested in what happens with time. And so we can think of EA as the applied voltage function of time. In a particular application, the applied voltage may be simply kept constant. In that case, EA will be just a constant function. Omega m is the angular speed function. IA is the armature current function. DIA is the function which is the result of differentiating the armature current function. And so this equation tells you that one function, the applied voltage function, is a sum of three other functions. Omega m multiplied by a coefficient or constant KB. KB is not a function of time. KB is unchanged with time. IA into RA, again RA is not changing with time. That's one of the assumptions that I am making, of course. In practice, the armature will get heated up, and depending on how much current it is carrying, the armature temperature will vary. Therefore, the armature resistance will not remain absolutely constant. The third term is the derivative of the current multiplied by the inductance, and I am assuming that the inductance does not change with time but remains constant. So instead of an equation relating the instantaneous values, we have an equation relating functions. We will use tools like the Laplace transformation or the Laplace transform for studying, analyzing, and for designing. And at that time, this kind of a way of looking at it will be useful. Instead of instantaneous values, think of function, behavior in time. So this is one equation, and the other is the mechanical equation, which says that the motor torque Tm, and I will not write therefore Tm at time t, but the function Tm equal to the load torque function TL plus the inertia related term, so J into d omega m, plus the third term which is Kf into omega. And of course I can, instead of Tm, I can directly have the armature current there, and so write it as Kt into Ia, because as I said, Tm is not going to be easy to measure, nor is it necessary to measure it. So we will have these two equations. Both of them involve derivatives. One of them involves the derivative of the current. In other words, when the current is changing, you have to take care of that fact by using that term. And the other equation involves the derivative of the angular speed. Therefore, when the speed of the motor is changing, for example, when the motor starts from rest and goes up to a certain speed, or the load is suddenly changed, therefore the speed of the motor changes. Then we have to consider this inertia term, which is related to the rate of change of speed. And as you can see, therefore, these two equations together look as if they are differential equations. They are differential equations involving the variable Ia, armature current, and the angular velocity omega m of the motor. And they are first order differential equations, because only first order derivatives of the armature current variable and the speed variable are occurring in these equations. So they are both first order differential equations. In both the equations, the only quantities that appear are the two quantities Ia omega m, whose derivatives appear, and the other two quantities Ea and TL. TL is the load part of it. Now this will play the role, or this is what can be thought of as a disturbance, in the sense TL may change suddenly in some unknown way. If you know what TL is going to be, then that's one thing. But suppose something happens and the load torque changes suddenly. So TL will be our disturbance variable. Although it's not really a disturbance, it's the reason why the system is in place. But about it we may not know as the drive actually proceeds. Something may happen and the load torque may change suddenly. The other variable, Ea, is the power supply voltage variable, and this we can think of as an input variable, because in our scheme, and I have called it armature controlled drive, we'll assume now that we'll control the motor by changing Ea if necessary. The load is driven by a motor and not cranked by some handle. The motor is controlled by changing the applied voltage, Ea. So the problem is now of how and when to change the applied voltage. We'll see that this TL not being known beforehand, or the possibility that TL may change, along with the fact that the motor parameters, the drive parameters that we have all listed, may not be known exactly. The back EMF and the torque constant, the armature resistance, armature inductance, the moment of inertia, the coefficient of friction, none of them of course are going to be known exactly with 100% accuracy. There will be some tolerance for each one of them. So that's one thing. The other is the load torque, uncertainty about the load torque. If it cannot be ensured that you know TL, what it is going to be, these two things will necessitate the use of feedback. That is, if we want the drive to perform satisfactorily, it is these two, the uncertainty in the parameter values and the disturbance aspect of the load, which perhaps can be reduced, the effect of these can be reduced by using feedback. And we will see what kind of feedback can be used and what is the effect of using feedback. But before we think of using feedback, we can do some preliminary calculations. Assumption that TL is known and omega, the desired angular speed, is known. That is, you want the load to run at a particular angular speed, and the load at that angular speed requires a certain amount of torque. And we'll assume that somehow the motor has been put in what may be called a steady state, the motor and the load, that is, the armature current, the velocity omega, the applied voltage Ea, and the load torque TL, all of them are going to remain absolutely constant. It's like the DC case, so to speak. All the variables are not really varying, but have remained constant. thanks to the circumstances, power supply voltage is remaining constant, load torque is not changing, and therefore the motor runs smoothly at some desired constant speed. So under this assumption of constant speed, constant applied voltage, constant torque, constant armature current, under these conditions we can make some calculations, then see what is the effect of changes or inaccuracy in the knowledge of the parameters, changes in the load torque, changes in the applied voltage, and so on, and then go on to the possibility of using feedback, various kinds of feedback, and so on.